Welcome, class. Welcome to your very first day of Intro to Machine Intelligence. I am absolutely thrilled to have you all here. So, in today's explainer, we are going to map out the entire architectural evolution of artificial intelligence. We'll be taking a look at exactly where this discipline started, the massive mathematical paradigm shifts that literally rewrote our software methodologies, and how we actually arrived at the astonishing foundation models we use today. Seriously, if you're entering the computer science field right now, you are stepping into an era where the lines between code, data, and autonomous reasoning are fundamentally blurring. It's a wildly exciting time. Okay, let's just dive right into it.
Here is the syllabus for today's lecture. First up, welcome to machine intelligence. Second, from symbols to networks. Third, the foundation model era. Fourth, AI and scientific discovery. And finally, number 5, trade-offs and future horizons. Let's get started.
Section 1. Welcome to Machine Intelligence, defining the field.
Well, before we can build anything, we really have to define our terms, right? Let's establish exactly what we mean when we talk about AI in the context of computer science, mostly because it is the absolute driving force behind digital transformation across every major industry today. So artificial intelligence, at its very core, refers to computer systems that simulate human intelligence to perform tasks autonomously. We're talking about things like reasoning, learning, and complex problem solving. Now, as computer scientists, we don't just build one giant monolithic AI, we build interconnected subfields. We leverage machine learning to allow systems to learn from data without explicit human programming. Then we integrate computer vision so machines can actually interpret visual information, and natural language processing so they can understand human language. And you know, the truly beautiful part is how all these elements combine hierarchically, which allows us to eventually build robotics and agents that can navigate both physical and virtual worlds.
Section 2. From symbols to networks, historical eras of AI.
So, we definitely didn't always rely on massive data sets to teach our machines. Our field has actually undergone some pretty massive paradigm shifts. Back in the 1950s and 60s, we heavily relied on what we call symbolic AI, which was totally dependent on explicit, human-coded logic. And while early attempts at data-driven learning did exist, like Frank Rosenblatt's perceptron way back in 1958, critics correctly pointed out that these early models just couldn't solve non-linearly separable problems. Think of things like the XOR logic gate. That limitation, along with a total failure to match the early hype, triggered the very first AI winter in the 1970s. From there, we moved through knowledge-based expert systems into statistical learning with support vector machines in the 90s, before finally entering the modern connectionist or deep learning era in the 2010s, which was all powered by big data and highly advanced GPUs.
Notice the comparison here, because that right there represents the core trade-off we made as an entire discipline. You've got to remember the no free lunch theorem in computer science. As we shifted from symbolic AI over to deep learning, we traded away something extremely valuable: explainability. You see, symbolic AI was highly explainable because literally every single rule was explicitly coded by a human. But the downside? It was computationally brittle out in the messy real world. Deep learning, on the other hand, gave us incredibly powerful automated feature extraction dependent on vast amounts of data. But the cost for all that power? We now struggle with black box explainability, where the actual internal reasoning of the model is completely obscured from us.
This automated feature extraction is driven by artificial neural networks. So instead of manual feature engineering, which, trust me, used to take researchers years to perfect, these networks use hidden layers of interconnected nodes. Each layer transforms the input data through complex mathematical operations. That deep learning, it literally refers to these multiple hidden layers automatically extracting higher-level features from raw data. And make no mistake, this was a total from-the-ground-up architectural rewrite of how we build intelligent software.
Section 3. The foundation model era. Massive scaling laws. Now, this shift towards neural networks eventually unlocked those massive scaling laws, bringing us to the absolute most critical architecture of your future careers. The key takeaway here is understanding what makes a foundation model so different. Historically, if you wanted an AI to, say, recognize a tumor, you trained a highly specific, computationally expensive model entirely from scratch on meticulously labeled medical data. Foundation models totally flip that paradigm. These are models trained on massive internet-scale amounts of unlabeled data. We are talking trillions of tokens here. Because they've learned generalized representations of language or physics or imagery, you can take just one of these foundational models and fine-tune it for a huge multitude of specific downstream tasks. This completely, dramatically lowers the data labeling requirements and totally democratizes AI research for much smaller teams.
I really want you to internalize this quote from Stanford's advanced CS curriculum. Conversation has become code, and the model is the CPU for this ultimate programming language. Think about that for a second. With systems like the GPT family and DeepSeek, natural language is now an execution interface. Large language models are essentially acting as generalized processors. You no longer just write Python to execute a task. You can literally write a conversational prompt, and the model translates your intent into highly complex, generalized execution steps. It's a real game changer.
And just look at how this workflow builds into modern logic. We are pushing way beyond mere pattern matching by using rule-based reinforcement learning to actually teach these models how to reason. The training recipe basically goes like this. First, you show the model a problem, like a complex math puzzle. Second, you ask it to produce a step-by-step chain of reasoning, or a chain of thought. Third, you apply a strict format reward or reinforcement only if the final answer and the logic are correct, severely penalizing any shortcuts. And then, you repeat this thousands and thousands of times. This shifts models from simply guessing the next word to reliably planning and acting as truly goal-oriented agents.
Section 4. AI in Scientific Discovery. AI as an accelerator.
Okay, let's move from the theory into practice and look at how these foundation models are acting as massive technology accelerators directly in the laboratory. Right now, we are witnessing an unprecedented convergence of AI and the hard sciences. I mean, DeepMind's AlphaFold famously solved the 3D protein folding problem that had stumped scientists for decades. But as of late 2025 and 2026, it goes so much further. We literally have AI co-scientists built on multi-agent architectures that are proposing entirely novel, validated epigenetic targets for diseases like liver fibrosis. In the gaming and simulation space, NVIDIA's nitrogen agent has shown a 52% higher success rate on unseen tasks simply by transferring skills across thousands of different environments. And frameworks like Agent Laboratory, they are successfully and autonomously reviewing dense literature and generating state-of-the-art machine learning code. And this right here brilliantly illustrates the real-world impact. A staggering 79 times efficiency boost. 79! In a recent collaboration between OpenAI and Red Queen Bio, GPT-5 was utilized to redesign and optimize an actual wet lab procedure. The AI didn't just crunch numbers, it fundamentally augmented the experimental benchwork, multiplying the output of the human scientists. That is absolutely incredible.
Furthermore, utilizing these LLM-based frameworks as autonomous research assistants has a massive economic impact. Studies on the Agent Laboratory framework, which is driven by models like O1 Preview, show that it can reduce overall scientific research expenses by 84%. That is a massive chunk of change. And more importantly, it frees up human researchers to focus on high-level creative ideation rather than getting bogged down in low-level coding and drafting.
But perhaps the most stunning milestone recently is the AI Scientist V2. This is an end-to-end agentic system that iteratively formulates its own scientific hypotheses, designs and runs virtual experiments, analyzes the data, and then actually authors the manuscript. When this was submitted to a rigorous human peer-reviewed ICLR workshop, it achieved scores that actually exceeded the average human acceptance threshold. AI agents are now successfully navigating the strict human peer review process entirely autonomously.
Section 5. Trade-offs and future horizons. Operational challenges.
However, as future engineers, you cannot just look at the glamorous successes. You have to understand the costs. Transitioning from traditional machine learning operations, or MLOps, to large language model operations, LLMOps, is a total paradigm shift. Actually, scratch that. It's a completely different beast. In MLOps, you were dealing with task-specific models, reasonable cloud compute requirements, and highly structured labeled data pipelines. But LLOps, that requires managing massive internet-scale text datasets and models with literally billions of parameters. This demands specialized, insanely expensive hardware like high-end GPU clusters. And critically, you are dealing with the severe output risks of confident hallucinations, prompt injection, and bias amplification. You are no longer just managing code, my friends, you are managing massive unpredictability. Take a look at this table. It clearly maps out the engineering realities you are going to face on the job. Look at the transition across the operational layers. Back in the deep learning era, the main risk was just overfitting your model to the training data. Today, in the foundation model era, your output risks include severe security threats like prompt injections and epistemic threats like hallucinations where the AI confidently and convincingly asserts completely false facts. So while foundation models offer immense game-changing power, they require rigorous safety benchmarking, intense human oversight, and frankly, massive energy consumption to run securely. We are essentially managing compound systems of immense, unprecedented complexity. As we wrap up this explainer today, I want to leave you with a rather profound question as you officially begin your journey in this rapidly accelerating field. If an agentic system can autonomously generate novel hypotheses, run the code, and publish a peer-reviewed scientific paper, well, what is your fundamental role as a human computer scientist today? The answer absolutely lies not in competing with these models on syntax or data recall, but in steering them. How will you partner with these systems? How will you govern their safety? And how will you push the boundaries of human knowledge responsibly? I highly encourage you to keep that in mind as you continue to learn the architecture behind the intelligence.